Welcome back to The Explainer. Okay, let's just jump right in because right now the James Webb Space Telescope is completely breaking the laws of physics as we know them. We're talking about discoveries that are quite literally forcing scientists to toss their textbooks out the window. From directly imaging the absolute lightest exoplanet we've ever seen, a huge milestone we're going to focus on today, to spotting early universe galaxies that are way too massive, way too soon. In this explainer, we're going to explore these impossible discoveries and see exactly how our understanding of the cosmos is being completely turned upside down.
But to really grasp just how crazy these findings are, we've got to start with a massive technical hurdle. Seriously, how do you photograph a planet that's trillions of miles away? Think about it for a second. Stars are blindingly bright, right? And planets are incredibly faint. Trying to see a planet right next to its host star is kind of like, well, it's like trying to spot a tiny firefly buzzing next to a lighthouse from miles away. It's notoriously difficult to directly image these exoplanets without our instruments just getting totally washed out by the massive glare.
But JWST just pulled off a monumental first. Just think about this number, 1. This represents the very first time Webb has directly imaged a lightweight Saturn-mass planet. It's called TWA 7b, orbiting a young star. Now, sure, we've imaged massive, bulky gas giants before, but TWA 7b is the lightest planet ever seen using this direct imaging technique. It's a total game changer. We aren't just looking at shadows anymore, guys. We're stepping into an era where we can finally look these distant, much smaller worlds directly in the eye. So let's move right into part 1, bizarre and impossible worlds. When looking at the data for an exoplanet named PSR J2322-2650b, Carnegie astronomer Peter Gao literally asked, "What the heck is this?" And honestly, it's a super fair question. This is a Jupiter-sized planet orbiting a rapidly spinning dead star, a pulsar. The gravity there is so intense, it's actually pulling the entire planet into a bizarre lemon shape. But the craziest part? Its atmosphere is made of pure molecular carbon. We're talking thick soot clouds floating around, and deep down inside, those clouds condense and literally rain diamonds. Out of 150 planets studied with JWST, 0 others have this kind of chemistry. It completely shatters every formation model we have. Then there's the ultimate rule breaker, TOI 561b. This is an ultra-hot super-Earth that whips around its star in just over 10 hours. Now, based on everything we knew, a small blistering planet like this should just be a bare rock with a surface temperature of around 4,900 degrees Fahrenheit. The star's radiation should have blasted any gas away eons ago. But here is the reality. JWST measured the temperature at only 3,200 degrees. That massive temperature drop means it has a thick atmosphere. No way around it. An atmosphere on a magma ocean world that is actively circulating heat and cooling its dayside. Just incredible. Let's keep exploring these wild atmospheres because you have to consider the rapid-fire daily weather cycle on WASP 94AB. It's a hot Jupiter, about 700 light-years away. JWST gave scientists the unprecedented ability to separately analyze the morning and evening sides of the planet, and the forecast is just insane. In the morning, the sky is packed with clouds made of magnesium silicate, basically literally rock-like mineral clouds. But as fierce winds sweep this air over to the ultra-hot day side, these rock clouds vaporize completely, leaving the evening skies totally clear. Plus, this high-precision data revealed its overall bulk chemistry is actually very Jupiter-like, which corrects all those older models that assumed it was packed with oxygen and carbon. So the absolutely crucial takeaway here is that planet formation is way, way more complex than we thought. Take TOI 5205b, for example. It's a Jupiter-sized gas giant, but it orbits a tiny red dwarf star that's only 40% the mass of our sun. According to all our models, a tiny star like that shouldn't even have enough leftover material to form a giant planet. And yet, there it is. Even weirder, JWST found its outer envelope is carbon-rich, but its deep interior is 10 times more metal-rich, with absolutely zero mixing between those layers. It proves that giant planets can somehow form around tiny stars with entirely separate, unmixed layers of chemistry. It fundamentally challenges how we think gas giants are built. Which brings us to part 2, breaking the early universe. Scientist Joel Leja perfectly summed up this next massive headache when he said it actually creates problems for science. See, JWST peered back roughly 13.5 billion years to when the universe was only 3% of its current age. Instead of finding small, chaotic, little baby galaxies like everyone expected, they found ultramassive objects that were just as mature as our own Milky Way. It's literally like looking into a nursery and finding fully grown adults hanging out in the cribs. It calls the entire timeline of how and when galaxies assembled into question. The universe apparently grew up way, way faster than anyone ever anticipated.
And, it's not just galaxies we're talking about, it's black holes, too. So how exactly did JWST manage to weigh a dormant black hole from over 10 billion light-years away? Well, it's like a cosmic relay race. First, a massive foreground galaxy cluster called Pandora's cluster physically bends space-time itself. Second, this warped space acts like a giant natural magnifying glass, stretching and amplifying the light from an object way behind it, in this case, a dormant black hole named MRG M0138. And finally, JWST's incredible near-spec instrument captures this faint signal, which was magnified a whopping 30 times over. This natural optical boost proved for the very first time that we can actually study the gravitational pull of black holes from the literal dawn of time. Speaking of the early universe, we also have the totally impossible discovery of JWST's quintet. Now, at a redshift of 6.71, which means very, very early in cosmic history, astronomers fully expect galaxies to be small and completely isolated. Instead, Webb spotted this highly chaotic, compact region where 5 distinct galaxies are just crashing into each other, all surrounded by this massive halo of oxygen-rich gas. It's a violent, gigantic merger happening at a time when the universe was supposed to be quiet and sparse. Moving right along to part 3, chemistry of the cosmos. What's really fascinating here is the stark chemical contrast sitting inside a single star system. In one area, we have the planetary forming disk around a host star, which has 0 detectable carbon molecules. None. But then, right nearby, in the moon-forming disk swirling around its baby gas giant, TWA, well, JWST detected 7 different carbon-bearing molecules in there, including benzene. It completely shocked researchers to see that the material making the moons is entirely different from the material making the planets right next door. It really suggests that these hyper-localized environments undergo incredibly rapid, accelerated chemical processing. And we're actually seeing this bizarre chemistry in objects visiting us from other star systems, too. Take the outgassing of interstellar comet 3I/8LIS, which was captured during a super cool coordinated observation by Europa Clipper, JUICE, and JWST. A massive 80% of its coma is made of carbon dioxide. Now, in a typical solar system comet, water vapor is what dominates. But this visitor from the cosmic void, it's basically a chemical time capsule, forcing scientists to completely rethink how objects form out there in distant stellar nurseries. Which connects us nicely to part 4, mysteries in our backyard. When scientists analyzed the actual physical samples brought back from asteroid Bennu, they found this rich broth of life's most essential chemical ingredients. The exact same complex carbon-bearing building blocks that JWST is detecting way out in those distant moon-forming disks and ancient interstellar comets, they are literally floating around on rocks right here in our own solar system. It shows this profound chemical connection across the entire universe. The basic ingredients for life and complex worlds are seemingly everywhere you look. But exploring our own backyard also comes with loss. Just think about the incredible decade-long journey of NASA's MAVEN orbiter. MAVEN arrived at Mars back in 2014 to study its atmosphere, and it made some truly unbelievable observations, like tracking how a global dust storm in 2018 lofted water molecules straight out into space. But sadly, in late 2025, an anomalous spin drained its batteries. And by June 2026, and honestly, MAVEN's entire legacy is perfectly encapsulated by this one number, 100 grams. MAVEN discovered that because Mars completely lacks a protective planetary magnetic field, the unyielding solar wind literally strips away 100 grams of its atmosphere every single second. And during solar storms, that rate jumps tenfold. This singular discovery finally explained the ultimate mystery of how Mars transformed from a warm, wet world that was totally capable of supporting liquid water into the freezing, dry desert we see today. Finally, let's wrap things up with part 5. The search continues. So here's the big question. If JWST and our fleet of spacecraft are rewriting the rules of the universe this fast, shattering our models of planet formation, galaxy evolution, and cosmic chemistry, what in the world are they going to find tomorrow? The textbooks aren't just being rewritten right now, they're being completely reinvented from scratch. Every impossible discovery we make just opens the door to 100 brand new questions. Thanks so much for joining me for this explainer. Keep questioning what you know, and I'll see you in the next one.